Hello and welcome to Func Prog Sweden, number 3 this year from the studio in Stockholm. Warm welcome. First, I would like to welcome all our recurring MeetUp guests. Warm welcome back to Func Prog Sweden, and to all new viewers, welcome to Func Prog Sweden. This is the MeetUp and YouTube channel where we explore functional programming, languages like Haskell, Erlang, Scala, Clojure, and more. And we've also explored different programming languages like C++, Java, and more, and how you can do functional in other languages. With that said, let's head over to today's agenda. First up, it's as always a short intro by me. Then we'll head over to an introduction to OCaml by Sudha. After that presentation, we'll head over to lessons learned by Mikael Tönnberg. But first, I would like to thank our video sponsor, Algebraic. Algebraic is an IT consultancy company based in Stockholm and have an office in Ho Chi Minh City also. Most of the developers in Algebraic have a background in functional programming. If you want to know more about Algebraic, please check them out on algebraic.com or in social media. Then for the continuation, the schedule. In May, we'll have another meetup, and then we are also planning for another meetup in June. So 23rd of May, next meetup, and then in June, we'll have another meetup. If you want to support the meetup community, which of course you want to do, you should head over to MeetUp and join the community, and you should follow us on YouTube and subscribe to our channel. And of course, join also our relatively newly started Discord server, Func Prog Sweden, where you can discuss with other people functional programming and the meetup of today. And also, if you want to get a t-shirt like this, head over to our merch store. You find the link on the meetup page or on the YouTube channel. If you have questions during the presentation, you either shoot them in the chat of YouTube, or you head over to the Discord server and shoot the different questions you might or might not have. With that said, let's start. Let's head over to our first presenter, Sudha. Hello, Sudha, and warm welcome to Func Prog Sweden.
Hello, Magnus. Can you hear me all right?
Yes, we hear you all right.
Great. Thank you. Thanks for the invite. I'm happy to be here.
Yeah, warm welcome.
And I suppose you can see my screen as well now.
Yes, we can. We see your screen nice
Great.
and well.
Great. Okay. Good evening. Yeah, I think it's evening for everyone. Yeah, good evening, everyone. Thanks for the invite, folks at Func Prog Sweden. It's great to be here. So today, what I'm going to talk about is an introduction to OCaml. I know that most of the people who are listening to this have some background in functional programming, and you have been doing functional programming in different languages. So what I'm going to try to do today is to convince you why it's a good idea to check out OCaml, even though you may not intend to do serious programming with OCaml. So that said, let us start. So first, who am I? I am a software engineer and team lead at Teradus. The Teradus is this open source software company where we do all things OCaml. We work on the OCaml compiler, we work on the OCaml platform, and the ecosystem as well. Right. So I have been personally hacking on OCaml since 2019. So it was in the late 2019 that I joined the team, multi-core OCaml team at IIT Madras, which is a university located in Chennai, India. So before that, I was a technology associate at a finance company called Northern Arc Capital. And even prior to that, I have a graduation in computer science and engineering from Chennai, India as well. So that was about me. So now let's get into the topic for the day. What is OCaml? I suppose some of you might have heard about OCaml in passing, or some of you might even be doing serious OCaml. But just to give a quick introduction to people who might be uninitiated, OCaml is an industrial strength functional programming language at its core. So it is derived from the meta language family of languages, which includes other languages like standard ML and so on. One unique thing about OCaml is that it also supports imperative and object-oriented programming. Although they are not the most popular features of OCaml, they are features that make OCaml a pragmatic and a more practical language for day-to-day use, right? So the next thing you might ask me is, do people actually use OCaml? So I know that oftentimes functional programming has this reputation of being academic or sort of historic languages which are used for very niche things, which might be true in some cases, but it is also true that OCaml is used in the industry quite a bit. Right. So these are some of the examples, and this is not an exhaustive list by any means. So just to give you some picture, Chain Street has been doing OCaml for more than a decade now, I believe. All their trading systems are written in OCaml. Uh, so if you look at the Tezos blockchain, their entire code base or the major part of it is for anything. It's possible that you are running OCaml code, right? So there are other companies like Lexity is this finance company that's based in Paris. They also have a lot of their systems running on OCaml. And they also have a lot of their systems running on Windows, which is a unique combination because OCaml sort of has a reputation of not being easy to use on Windows, which is, I'm happy to say, changing quite a bit in the recent days. OCaml is also used at Meta, Bloomberg, etc. So Meta has quite a few interesting projects written on OCaml. They have this static analyzer. It's a static analysis framework they use internally for things like code reviews. They also have a extension of PHP, which has types, and that is also written in OCaml. And of course, Tarot is where I work at. We do a lot of OCaml stuff, and most notably, we have projects like Irmin, which is data store that's written in OCaml, and also Mirage and the ecosystem surrounding Mirage. So Mirage, in its core, is a unikernel operating system. There are lots of pure OCaml Mirage libraries for the network stack and so on. So this is just to give a picture on where and how OCaml is used, right? So with that, let's dive into OCaml. So this is just a very quick introduction of what is function programming. I'm sure a lot of you might be familiar with this already. Right. So functions are treated as first class citizens. That's the essence of it. And this is inspired from lambda calculus. The lambda calculus is this way to express computing, which is was then proved to be equivalent with Turing machines. So lambda calculus was invented by Alonzo Church, who was the advisor of Alan Turing, who came up with the Turing machines. So Lisp was the very first functional programming language that was used. And this was the first version of Lisp was built by John McCarthy, who's also known as the father of artificial intelligence. So there are other functional programming languages which I'm sure a lot of you might know already: Haskell, Scheme, Clojure, Scala, etc., etc. So now another important question to ask here is why should I learn OCaml, or even why should I learn functional programming? So programming languages matter. They affect the way you think. So this is a quote by Alan Perels, who was the first winner of the Turing Award. Uh, so Alan Perels puts it very nicely. He says a language that doesn't affect the way you think about programming is not worth knowing. So in the rest of the talk, I'm going to try to convince you why OCaml is worth knowing. Right. So before we dive into that, I just want to point out something. Functional programming has, in the past, predicted future, going by the evidence we have. So if you look at some things that came into existence in functional programming quite a while ago, like take the first example, garbage collection. Garbage collection is the mechanism of collecting, freeing data that's not being used. So this makes the life of a programmer a lot easier, because the programmer is no longer expected to, manage the memory by themselves. If you're writing programs in something like C, it's on the programmer to manage memory with things like malloc or free or any other allocator. But a managed programming language with garbage collection takes the burden off from the programmer. So in turn, the programmer becomes more productive in writing programs. I know this is a very simplistic way to look at it, but this is true for most practical purposes. So garbage collection came into existence in Java in the late 90s, 1995 to be precise. But if you see the origins of garbage collection, it was introduced way back in the 1950s in Lisp. Similar case with higher order functions. In fact, it took longer for Java or other mainstream languages to pick that up. But again, Lisp had higher order functions way back in the 1950s. Some other features that are becoming more and more famous in mainstream programming languages is type inference and generics. Again, that was introduced in 1990 by standard ML. So if we are to go by this, it's possible that more mainstream languages start adopting more and more functional features. So not only functional programming makes you think better about the way you write programs, it might also be useful in the future when you're writing mainstream languages like Java or C++ or C Sharp or Go and whatnot. So the next question is why OCaml? Now that we are sort of convinced why functional programming is worth knowing. So let's step back a bit and ask ourselves, who are we writing programs for? Of course, programs are going to be run in machines, and we have all sorts of architectures in the machines that are going to be used in different places. So your Linux machine might have a different architecture. Your Mac has a different architecture. You're running your code on a server that again has a different architecture. But all those details are abstracted out to us by this wonderful software called the compiler. But end of the day, the program you write is going to be directly read by humans. They might be your co-workers, they might be your collaborators you're working on with your project, might be your friends. So whoever it is end of the day humans who are going to read the program. So it definitely makes sense for us to optimize the human interaction part of programming. So OCaml or even functional programming in general lets you write elegant programs. We'll see how. So some of the notable features of OCaml are these. Very quickly, uh, OCaml, in its essence, encourages immutability. Of course, there is room for mutable code. As I mentioned earlier, OCaml allows imperative programming, but that's not the norm. That's more of an exception for some sort of writing efficient programs or other use cases where it's unavoidable. It's definitely not the norm. OCaml also supports algebraic data types and pattern matching on the algebraic data types. It, of course, supports higher order functions. It has this type inference system based on the Hindley-Milner type inference system. So, what that means is the compiler is going to take care of the types for you. So the programmer is not expected to, give the types to the program. It's the other way around. On top of all these nice things we get from the functional programming world, OCaml is also good for systems programming, surprisingly. We'll see why later in the talk. Uh, and in addition to that, OCaml also has a performant garbage collector. So, in essence, the programmer need not worry about uh, memory management. The collector takes care of it for you, and it's also performant, so you don't see any notable performance degradation due to having a garbage collector. Right. So let's see all these features one by one. First is immutability. So by immutability, what we mean is variables do not vary, right? This might be counterintuitive for someone who's used to doing imperative programming, but I promise you, you will never want to go back from this if you get used to this. Uh, when variables don't vary, it also means that there are no side effects. Side effect in the sense there are no changes to the state of your program, and this means that debugging is a lot easier. That's the essence of it. I'll show you an example how. So let's say we have a list and we want to find the length of a list, right? Let's say we are writing a program in Python to do that. What would we do? We uh, have this variable length which is initialized to 0. And to find the length of the list, all you have to do is loop through the list and increment the value of length as you traverse through the list. So once you have gone through all the elements, you get the total length of the list and done. It very simple. So how do we actually do it when you don't have mutable variables? Because if you see, we are actually changing the value of length in every iteration. So to do it in a functional way, what we would do is we would recurse through the list. So this is where pattern matching comes in handy, right? So you match the list with two possibilities, right? One possibility is that the list is empty. If that is the case, the length of the list is 0, which is straightforward. So the other case is the list has some elements, right? And we don't know how many elements, but all we know is it has a head, which is X, and it has a rest of the list, which is XS. So all we have to do is we have to account for this X, which is the head. So that accounts for one element in the list, and find the length of the rest of the list, right? And this is going to give us the length of the list when we recurse through the entire list. If you compare it with the Python version, the idea is similar. The difference is what we do in the Python version is we traverse through the list using using looping, where you start from 0, which is the start of the list, and go till whatever the length of the list is. We do the reverse of it here, which is we recurse through the list. But in essence, it's the same computation. So if you remember, I mentioned something about type inference. If you see this type signature in the end, what it says is val length. So length is a function that takes in a list. So read this as quote list. So it means so quote is basically polymorphic type, right? So it can be any type. So what that means is your list can be a list of integers, or it can be a list of strings, or it can be a list of floats, or it can be a list of some more complex data structure. Doesn't matter, but it's a list, and the length of the list is going to return an integer. This was actually inferred by the compiler. So the powerful type system gives us this ability to infer type by the compiler. So we don't have to go through it. And more often than not, it's intuitive to see from the type what a function does, right? So this is the interesting part, right, where you match the list with the possibilities. So the next bit is type system again. There are, of course, base types like integers, string, float, etc., etc. But OCaml also has nice ways to construct types on our own. So one of them is sum types, where you can specify n number of constructors that belong to your type. So let's say we want to encapsulate days of a week as a type. All you have to do is create a new constructor for every day. So if you see here, we have a separate type for Sunday, Monday, Tuesday, etc. So this is known as sum type, where every type has a distinct constructor. So there are also product types, which are, in other words, tuples, right? So let's say we want to represent a coordinate point in a type. So this can be done as a tuple, where you have a value which is a collection of float and a float. So the left float can stand for x-axis, and the right float can stand for the y-axis, and so on. But we can also construct more complex data types with the algebraic data types. So here's an example. So let's say we want to construct a binary tree. This is all you need to construct a binary tree. So you create a type alpha of tree. What that means is your tree can store values of any type. And it has two possibilities, right? So the first one is the tree can be empty, which means it's a leaf, and the tree can have a node. What does the node have? So if you observe, this node is again a tuple, right? So it has one value that belongs to the node, and it also has the left subtree and right subtree. Right? This is all we have to do to define a binary tree. How do we actually use this? Right? So if you see the first example, one is a binary tree with just one node. So it has just the number one, and the left and right subtrees are empty. Right? We can use this as a building block to construct more complex trees. So if you see the second tree, it has two as the element, and it has one as its left and right subtree. We can keep building more and more complex trees this way. But let's say we want to compute the height of a binary tree. How do we do this? Again, pattern matching comes to the rescue. So height of the tree, we can compute it by matching the tree with its two possibilities. One possibility is the tree is empty, which means the height of the tree is 0. It can also be a node, which means the node contributes to height 1. And uh, the next part is that to compute the height of the tree, we need the maximum of either the left subtree or the right subtree. So, which is what we do here. We get the maximum of the recursion. We compute both the height of the left and right, and we take the maximum value. So this, in the end, gives us the height of the whole tree. So there are more things we can do with pattern matching, right? For example, let's say we want to compute the pre-order listing of a binary tree. This is all. This is all we have to do. If it's empty, it means we don't have a pre-order value. If it has a node, it means we compute the value first and then compute the pre-order value of the left subtree and then the right subtree. Right. Similarly, the order changes for in order and post order, but the idea remains the same. So what I'm trying to show here with this is that pattern matching makes it very easy for us to write expressive programs. Uh, so next comes higher order functions. So functions are treated like values in its core. So that means we can pass around functions as we pass around arguments usually. To give a small example, let's say we write a function multiply. It's an inbuilt function, but just to give an example, let's say we have a function multiply x5, and let's say we want a function double that just computes the double of a given value. All we have to do is use just the first argument of multiplying. What that does to when you use double is that this double is again evaluated as multiply 2. So we would automatically get the argument multiplied by 2. So it's 2 here, so this is 4. Let's say if it's 10 here, it's going to be 20. So this this gives us nice way to reduce code duplication. So there are more higher order functions. So one of the commonly used higher order functions is compose, which is basically just the mathematical compose where you apply one function first and then apply the result to another function. So compose f, g, x, where f and g are two different functions or two separate functions. So, and x is an argument. It is just f of g of x, right? To have a real example, let's say we have a function double that we saw earlier. We have another function square, which is just square of an integer value. So let's say we want to compute the double of a value and then square it. All we have to do is use this compose function to compose these two separate functions. This gives us the ability to write more powerful functions like, say, map. Map is a well-known function programming construct, I'm sure. So map, in its essence, gives us the ability to iterate through the list without looping through it, right? So if you take a function f, and in this case, I'm taking a list L, it need not necessarily be a list. It can be any collection, right? So what we do is we just recurse through the list and apply the function f to every element of the list. This returns us a returns us another list which has the applied values of every element of the list with this function f. So this gives us the ability to write more complex things and express more complex things with simple functions like map, fold, etc. So that was a quick overview of the different features of OCaml. Let's also see some other things that are inbuilt, right? Garbage collection for one. So OCaml comes with a performant garbage collector. It has been extensively benchmarked and tested. Uh, like I mentioned earlier, there are lots of performance sensitive applications written in OCaml. It's very important that the garbage collector is not a source of bottleneck for this. So what the garbage collector does is that it uses a generational scheme. What does it mean? It means there are two heaps where we can allocate values. There is one major heap which is larger in slice, and there is a minor heap which is quite small in size. By default, it's something like 2 MB, so it's not that big, but it works because as we saw earlier, a lot of OCaml code is purely functional, which means most of the values are not long lived. So that means they are collected quite soon. So the small minor heap gives us the ability to do fast allocation and fast collection both. It has a very simple allocation scheme. All it needs to do is it has to increment one value to allocate some value in the minor heap. And collection is again, it's a mark and sweep collector. The details are not important, but it's quite fast. The larger values are allocated in the major heap, and also the values that are long lived in the minor heap are copied to the major heap. So since the major heap is larger in size, the collection is done in slices. So it's not done all at once. It's split into smaller computations so that the garbage collector doesn't put a stop to the program for a long time. So this has been how it has been working for a very long time. Uh, Quite recently, December last year, there was a release of OCaml with multi-core support, which was the OCaml version 5. It was a major bump from 4.14. So the difference between the two is, of course, multi-core OCaml gives us the ability to write multi-core programs, and it also ships with a multi-core capable GC, because unless we do that, we have the risk of slowing down the programs due to GC bottlenecks, which is not great. So I'll talk about multi-core OCaml in a bit, but in a sense, this was the major challenge of multi-core OCaml. And like I mentioned earlier, OCaml has this unique way of supporting systems programming from typed functional language. So it has first-class support for Unix programming, and it also has a lot of concurrency libraries, monadic concurrency libraries, and direct style concurrency libraries. So to enable system programming, it has a highly performant CFFI. So it's practically quite straightforward to call C programs from OCaml programs. And a lot of C libraries have bindings in OCaml in effect. Why would we want to do that? Why not just use the C library directly? That's because writing OCaml bindings for the C functions is going to also give us the ability to use the strong type system that ships with OCaml. So it is like the best of both worlds, to put it in a simple way. Let's quickly take a tour through the OCaml platform. OCaml platform has improved quite a bit in the past few years. So the first thing is OPAM. OPAM is the package manager for OCaml. So if you want to install OCaml, this is where you start. I'm sorry I didn't paste the link here, but it's just one single script that lets you install OPAM in any system that you're using, no matter it's a Linux-based system or a Mac-based system or Windows system. So OPAM supports multiple compiler installations. And OPAM is also the single source package manager for your entire system. All the libraries are released in OPAM for wider use. So it's nice to have a single place where you can get all the packages that you need. Next comes the build system. So Dune is the most popular build system for OCaml. It is a composable system in the sense it's easy to use multiple projects together when all of them use Dune. This is an example of how a Dune-based project would look like. So this Dune project is what indicates the source file, which means this project name, whatever your project is, that's going to be the source. And this in turn has multiple things internally. For example, in this case, lib is the main place where you have all the library functions. Binary has the binary files. Test, of course, has the tests, and all of this is being managed by Doom. If you observe, there's also this package named at OPAM, which is the file that goes into the central repository of OPAM. So OPAM and Dune, in a sense, work together to provide a seamless build experience. So another important tool is UTOP. To me personally, it was quite useful as a learning tool. So UTOP is a nicer top level, right? I hope this is visible. Yeah. So this is a more nicer top level than the default one that ships with the compiler. In a sense, this handles concurrent requests and such. So this is basically a REPL, which is a nice way to just experiment with stuff, especially when we are starting out. There are more tools to improve your developer experience. I'm not going to get into all of them, but some of them that are quite useful are one is Merlin. Merlin is this code completion tool that we usually have in things like IDEs. When, for example, you use Java with Eclipse, those kind of mature IDE systems. So Merlin gives us the ability to do that. That's actually quite nice when you're working with large projects, right? And there's also OCaml format that does code formatting in a uniform way. So it's both easier to read and it's also easier to maintain. There are a lot more tools part of OCaml platform. I would encourage you to check out if you're interested. So I'll talk about multi-core OCaml very quickly. OCaml 5 is the first version of OCaml that added support for parallelism and concurrency. First, let me try to define what I mean by parallelism and concurrency. So, by concurrency, what I mean is overlap computations, right? So, let's say we have two different computations, A and B, happening. When they are concurrent, it means A and B happen in an overlap fashion where A gives up control, B takes over, B gives up control, A takes over, and so on. There are various schemes of doing this, but leaving that aside, the essence is that it's not the case the computation B starts only after computation A is over. It's possible to do both in interleaved fashion. So that is what I mean by concurrency. Parallelism is when they run simultaneously, right? The two computations we have are A and D. So if they run on two different CPU cores in a machine, it means they are running in parallel because they are happening in the same time. So there are two different topics. They work together to write scalable applications. To give a very quick history of multi-core OCaml, it started in 2014 at University of Cambridge, and then a lot more people joined in. People at OCaml Labs at Cambridge, IIT Madras at Chennai, India, and folks from Taradis at Paris. It was a collaborative effort with the core development team of OCaml, who are also distributed across the world. Uh, the major challenge was to develop a multi-core capable garbage collector and also to maintain backwards compatibility both in terms of features as well as performance. Uh, OCaml made the choice of having one single runtime and one single garbage collector for both sequential programs as well as parallel programs. This is not the case if you take, say, for example, languages like Haskell. Haskell has two different runtimes, right? One for parallel multi-core programs and another runtime for sequential programs, which is very useful if we want the optimized versions for both, right? So the runtime sequential runtime is optimized for sequential programs, and the parallel runtime is optimized for parallel programs. But this sort of increases the burden of maintaining both runtimes at the same time. So OCaml made the choice of having one single runtime. So what this meant was it's important to have backwards compatibility both in terms of performance and in terms of the features available in the sequential version of OCaml, because there are lots of performance sensitive applications running on OCaml today in the sequential version of OCaml. So for all those applications, they shouldn't take a huge hit in terms of performance when they switch to multi-core OCaml. This was the reason on the emphasis of backwards compatibility. So OCaml 5 was released quite recently in December last year, like I mentioned earlier. So if you're interested what this means, I definitely encourage you to check out all the nice things that ship with OCaml 5. But very quickly, the major features are domains for parallelism and effect handlers for concurrency. So domains are basically heavyweight threads. They're heavyweight because they have a minor heap of their own, right? And they are also mapped one-on-one with operating system threads, which are key threads. A new domain, when you create it, it runs in parallel with the domain that created it. And the domain interface in itself is very simple. It only has spawn and join for creating and destroying new domains. It has atomic operations so that they are safe to be executed in a multi-core context without races. And it also has local storage for quick access of some things that we might want to use only in a particular domain or thread. Uh, the other nice feature that ships with multi-core OCaml, regardless of whether we want to run it on a single core or multiple cores, is effect handlers for concurrency. So think of effect handlers as something like exception handlers, but only that uh, they have the ability to be continued later with with a delimited continuation, which means you provide a value to the continuation to be continued at a later point. So this is quite a simple idea, but it gives us very powerful abstractions for writing concurrent programs. If you're keen to know how this happens, I would definitely encourage you to check out the various examples we have with writing concurrent programs using effect handlers. So this was the major features that shipped with multi-core OCaml. I unfortunately don't have the time to go through the details in this talk, but I definitely encourage folks who are interested to check it out. With that, I think I've said all that I wanted to say in this talk. I'm happy to take any questions if there are any.
Thank you very much, Sudha. Thank you very much for your
Thank you.
great presentation. Thank you. No questions so far in the chat. However, I have some questions. How come you started with functional programming and OCaml? What led you into that path?
You mean me?
Yeah.
Personally?
Yes, you personally.
Right. Okay, so it's quite interesting in a sense. I used to do functional programming as a hobby when I was in my undergrad. Uh, so, but once I started working in the industry, I was doing something else. I mean, I was a Java programmer, but then I got the opportunity to work in the multi-core OCaml team, which is when I started learning OCaml, and I haven't gone back ever since.
Totally understand. Have you tried any other functional programming language, or have you only gone with or tried or worked with OCaml so far?
Yes, I have worked quite a bit with Haskell, and for my own projects, I haven't worked anything professionally. I have also dabbled a bit with different scheme dialects, Clojure, and other more experimental scheme dialects like Racket. And there is one called Callisto scheme that's written in Python. I have used this basically to go through this book, Structure and Interpretation of Computer Programs, SICP.
Yeah.
Which is also something I would definitely recommend people to do if they are interested.
Yes, I have one question. Do you have any general feeling on execution performance between OCaml and GHC?
And GHC.
Yeah, I don't know either what GHC stands for.
GHC is Glasgow Haskell
Oh,
compiler.
yes, it is.
Yeah, that's an interesting question. I think we should be careful here in the sense we should compare apples with apples and not apples with oranges. So GHC in its core is a lazy language. OCaml is not. OCaml is an eagerly evaluated language. So that is one major difference. There's something called computer languages benchmarking game, which was started for similar reasons. So it's a suite of different benchmarks that are written in a lot of programming languages. I'm sure we can find GHC and OCaml there. But again, we should be careful to compare apples to apples and oranges to oranges, not apples to oranges. So that is what I would add here.
Yes. And another question, one of the meetup guests wonder, like maybe you said it, but he missed it. How do you communicate between threads in OCaml in a multi-core environment, or how would you typically communicate between threads in a multi-core OCaml?
Right. So the multi-core OCaml comes with shared memory parallelism. That means the general values that you have are accessible by all the threads. This kind of gives you the ability to communicate between threads automatically. But we have more concurrency abstractions that are built on top of the compiler. And all of them have communication channels. Like, so for example, there is this library we built called domainslib, which gives us features for nested parallelism. And we have something called channels there, which you can imagine as something similar to ghost channels or GHC's MBARS. So some of these things are specific to the concurrency abstraction we use. But one topic of research has been how to generalize this for all the different concurrency abstractions we have. And we have made some progress on that with, again, effect handlers. So we are trying to come up with a generic solution for this, which should be used in practice soon.
Hmm? Thank you again. Thank you very much. And also to the audience and everyone, we'll share all the links. You had like a nice presentation. I saw the link online, so we'll share it. We'll publish the links and everything once we're done with the stream, so everyone can see your presentation and any other links you have. Sudha, you said you had like a link to some of the compilers, I think, and we'll share them also. Again, thank you very much for your presentation. With that, we will head over to our next presentation of the day. We'll head over to Mikael and lessons learned. Welcome, Mikael, to Func Prog Sweden.
Yes, thank you.
Yeah, you're welcome.
Yes. So let me share my presentation. There we go. Does it work? Yes, it seems like it works. Cool. Yeah, so I'm gonna talk a bit about some lessons learned from Carbon Cloud. Very briefly, the contents for today. First, I will do a short intro, talk about the good parts we experienced so far, some bad parts, some non-issues that I thought were going to be issues when we started out, and spend the main focus for today on reflections on testing. So I'm from Carbon Cloud. We are the climate intelligence platform. We do climate calculation primarily for food, and we have our open source, our open database for everyone that are interested in climate performance that can go and check that out. So I'm Mikael. I'm the co-founder and CTO of Carbon Cloud. And we have event source back in Haskell for all our applications, aside from some ML training stuff, some science stuff, and the AWS stack. But the main part of the application logic is in Haskell. Our frontends are written in Elm, and we have some browser testing in PureScript as well. And we have been working with these applications for what's it like 3-4 years now, and so far it's working out great. So yeah, we start with the last one, it seems. Yeah, so we have very few hard to reason about bugs. Of course, we have bugs. There are not very many, but we have them. But often they are really, really easy to squash when they happen. But the first thing on our list, we are very happy with our choices. When we started, that was both Haskell and Elm were not like the mainstream languages, are still not. But I would say I would do the same choices again overall. It's really stable. Our applications and our changes, it allows for us to iterate quite a lot. Both on the Elm and Haskell side, with all the key benefits they have, it's really easy to refactor. The team is actually refactoring a big integral part of the application in our biggest application as we right now, and improving that, solving a few main shortcomings. We have done so several times during the years, and had no major problems with that. One key thing is we have a really good performance out of the box without really needing to like optimize things in details. We have made some more systemic optimizations, like changing how the flow of the application or the calculation goes, which has improved performance. But in general, performance is nothing we have had the need to focus on that much. It's been a few bottlenecks, and we have had quite aggressive growth when it comes to both the customers and data in the platform. So we still had to have a work with performance from time to time, but it's not been a general thing then. So that's good. It's a real joy to not having some major problems like null checks and stuff like that, and just have them removed by design, which is really neat. As I said, we use event sourcing, which in my mind gives us superpowers. We can solve a lot of really difficult problems, or that would be difficult in other setups, really easy. Of course, it's not a free lunch. It adds some fundamental complexity, and we need to work with, you know, butterfly effects when we change the projections of the events and stuff like that. But in general, I'd say that's one of key things, key decisions we made from day zero that has really benefited us. One thing, and this is more Haskell specific, but also would apply to Elm, is that even if a package can be really, really old, like in software sense, like 6 years old or something, they quite often still work. The problems they solve, because and that, I think that is a general theme with these languages, that most, if not all, things stay solved if you don't want to change it actively, which is really, really nice. And I know each of these we could talk about at length, but I will just go paint with a broad brush, and then we'll go into today's topic. Yeah, and of course, not everything is great. One thing when compared to more mainstream languages is there are fewer maintained packages for niche applications. I don't think we have had like any major roadblocks when it comes to missing packages. So I wouldn't say that it's a blocker, but it's a comparative like difference, right? If you compare it to like the .NET platform or Java, or whatever, or Node or whatever. So there are fewer packages, and especially if you go to integrations with other services, or other platforms like SDKs and clients and stuff, there are fewer of those. As I said, it's not been a hard blocker, but you have to acknowledge that that's a difference if you compare to mainstream languages. And connected to that, like fewer turnkey solutions. For instance, if we set up a really easy to use SDKs for different, for the AWS, there are few, but they are few, and maybe not always up to date for the different packages, or not as battle tested in some cases as others. So and you have to like glue some pieces together yourselves. This is, I put it in bad, and this is Elm specific, but it's not worse than anything else comparatively. Like Vec Redux or something like that. It's just that the benefits of Elm with the state, without going into much detail, if you don't know Elm, it's a very opinionated both language, and it's a language and framework in one. It's very specifically tailored to do web applications, and you do it by having view a model and then updates and messages to. So you something happens in the UI. It sends a message, and then you have the logic, or you push the button, the counter button, or increase the counter with 1, and then it's re-rendered with a new counter value. That loop doesn't work if you want to have a lot of animations, because then if you use that loop, you will be CPU bound and not be able to use CSS3 in that way. I mean, you can do that, but you will do that outside that loop. So it doesn't make it worse than alternatives, but you don't get the full advantage of Elm. So I wouldn't. So it's not. It's not worse than others, but it's not as good as if you don't do those things. This is a Haskell specific one. Again, we have had very few hard to squash bugs. We have especially one that was really difficult, and it took a long time to understand what happened and why. And it was for some events we had a cache when it talked to the database, and the first implementation were really easy and simple, but with a high throughput of data, we got some race conditions and we couldn't understand why. And after a long time, we understood that it was a bug in the library. But to understand that and what happened when and why, what was the bottleneck and stuff like that can be really tricky when you have lazy evaluation. But they are rare and far between. This is bad concept. I said that the joy of not be able, the joy of not having those concepts in other languages that I personally think creates a lot of problems. If you simulate those in Haskell, you will still have the same problems. Like if you have a global state monad, we don't, but or if you create an interface, for instance, it doesn't matter if you like create a mathematical nice framework or a monad above it. If the concept's still the same, it will generate the same problems, even though it's better. The fundamental problem's still there. But it's good because those concepts are quite. You have to actively try to reconstruct those. So just because you do something in Haskell doesn't mean it's good if you import the problems from another language or paradigm. A few things that I saw as risks or that I thought would be a problem when we started this, when we took this choice. And two things came to mind. I think maybe there are more, but one thing was the style of documentation, especially in Haskell, is if you compare it to other languages, it looks really bad. It's in most cases, very little information aside from the type signatures. And I thought that was going to be a problem when we started to working with new libraries and stuff. Turns out that is a totally non-issue, at least for us, because the types are so important and tell so much. So I find it much easier doing it that way. So now if I do a small like scripting thing in Python or Node to do some import or stuff, and I use a library, I tend to see the nice human language documentation to be just in the way, and I try to find the actual meat okay, what is the parameters and what's the behavior. So that's been a known issue. The other one I also mentioned because it seems to be a big thing that many are a roadblock many people like encounter when they try to introduce these types of tools in the workplace. I've heard it from several people. Is the hiring would be so difficult. For us, it hasn't. I would say, of course, there are fewer than mainstream languages. So in numbers, it's much harder, but in the outcome or the how much we've been worked to get good hires, I would say is the same. And I would say that the average level of competence of the people that apply are much higher. So I wouldn't say that hiring is a factor when it comes to this, the choice of using Haskell or Elm or something like that. Cool. So with that, and again, all of those points before we could talk quite at length about, but I wanted to focus a bit on testing. And there's a lot of things to say about testing. First of all, I think it's for us, it's really important that things work as intended. We put quite a lot of effort into that. You can ensure that in different ways. And I want to present one way to think about it. I don't suppose that's the only way to think about this, but I think it's a tool at least. When you have finite resources, you want to put them where it matters most. So I will go through some concepts and then some tools, and then we're going to put it all together to see and present why I think working with languages with really strong type systems are really important and helps us in a commercial sense and a business sense. And I think it's benefits and advantage to do so if compared to other or other choices. Yeah, so this one thing that I as a person likes about Haskell, there's a lot of rigorous thinking to solve problems, but also I think that can come in the way sometimes, because most of us, me included, just want to use the tools and languages to produce cool things, right? So I will try to not to focus on rigorous definitions and stuff like that, but I still want to explain a few concepts to convey the fundamental idea, hopefully. So I will be, if you have a lot of background in these areas and thinks I'm not as precise as I should be in some places, you are right. But I think it helps this rather than hurt it. So first off, it's concept of cardinality. And that is the number of different unique values something can have, meaning you can think about if you have a switch statement or a case-off statement, it's the number of, if you want to uniquely pattern match on each value that that thing can have, how many state rows do you need to match on? So a bool has a cardinality of 2 because it can be either true or false. There are no other values. And a string has the conceptual cardinality of, like, it's an infinite range, right? Because you can always add another letter and continue that, and all of those will be unique. And either bool, meaning, and either it's a left and true false, or right or true false. So that's a cardinality of 4. 4 different unique states. And if you want to test something, test a function, the higher cardinality it has, the more demanding to test it will be. Meaning that if you have a function that takes no argument, and if it's pure, now we're talking about only pure functions, meaning functions that doesn't work with side effects. Then if you have 0 arguments, then you need only to write one test, right? Because you're always going to get the same value. And if you have a function that has only a bool as input, then there's only 2 tests that needs to be written, right? And if you have a string and you want to test that completely, if you just do it the most naive way, you want to test, okay, if I call function x with the input of a and then b and c and then a and bb and etc., then you will, since the string has a cardinality of infinite cardinality, you will have to write an infinite amount of tests, right? If you want to test it completely. So cardinality is one concept, and other one is arity, is simply the number of arguments to a function. This is ignoring the language implementation, but as a mathematical sense, or how the things are perceived. So if you have the function add, it takes 2 numbers and add them together. It's an arity of 2 because it takes 2 arguments. And again here, and I think that it feels quite intuitive, is that the higher everything else equal, the higher arity numbers, or the higher arity of a function, the harder it will be to test. Because if you have only one bool as input, you have two different paths to go down. But if you take 100 bools, right, you have a lot of different combinations that can yield different types of results. So when we combine those two, the behaviors is in a very precise, specific way. So if we want to calculate the total cardinality of a function, it's the product of the cardinality of all parameters. Meaning, if you have a function that takes 2 bools, then you have one bool can be in 2 different states, but for each value of the first, it can be 2 from the other, so it's 4, right? So if we have add, and assuming 32 bits integer, we have 2 to the power of 32 times 2 to the power of 32, which is pretty large, right? So in this sense, the arity affects the total cardinality a lot, since if we add, let's say the either has 2 cases, it could be either left or right. If we add a third option there, then it will be only increase it by 1, right? But if we add another parameter, we're gonna the cardinality will increase by taking the product of those 2 things. And here I can say that there is no, when it comes to cardinality, doesn't matter how the data is structured in language. If it's a function that just take one value after the other, or if it takes one thing that is a record with 10 things, that doesn't really matter, right? Because the total cardinality will be the same. You have just reshuffled those 10 values into a single record, but the total different permutations the input can have is still the same. And again here, so with the higher the total cardinality, the more to test. This can also be a good tool when refactoring types. If you do something and the cardinality changes, then you have changed the behavior. Since if you want to, or then at least you mostly have not intended to, you most likely have made a change you haven't intended. So that could be a good way if you have a more complex type and you want to rearrange things, for example, from a nested record and we want to flatten it, then the cardinality will stay the same. If you don't do some kind of mapping between the different types, but that's a like corner case. So we have a total cardinality, and the basic correlation is the higher the cardinality, the more effort we need to put into testing if we want to be ensure it makes the correct things, right? So I don't really like this headline, but like correctness tools, like things or activities or tools that we can use to ensure that the program does what we want to do. There are a lot of different things. This is not I won't present exhausting lists here, but we can do example-based tests, which is just like add 3 and 2 should equal to 5. You just take a specific permutation of the inputs and say that with this input, I want this behavior or this output. We can have property-based tests, and in this case, add x and y should equal to add y and x. I'll go into each of these specific individually, but I just want to throw them out there at the start so we can. Or we could avoid the need to test that particular thing, right? And here we could do a lot of different things. We could throw out the implementation and if that feature is not needed, or if we can find a way to make that step so we don't need to do that compute. Or we can change the implementation to make the test irrelevant, and what that means we're going to talk about more later. So example-based tests corresponds, I think, closely to what people think of when they hear the term unit tests. But I think that more specific, for me, more specify the level of where in the application you test or what kind of scope you aim to cover with the test. So that's why I use this example-based test title instead, just to make sure when you compare to other types of tests. Instead of you can do an example-based test on like system level or API level, or you can do it on a function, right? All the principles will still be valid that I will go through. So example-based test is like add 3 and 5 should be 8, if my math is correct. So a benefit is that it's really specific, right? You as a developer, or AI, if you use that to write your test, specify a specific permutation and can say that regardless how the implementation looks like, I want this as a specific outcome. So it's very specific and concrete. You can see, is this correct? I don't need to go up abstraction and try to explain the behavior in a more generic or abstract way. I can say that with this input, I want this output. And I think it's quite easy to start writing these because you don't need to have create a fully complete model of the domain or something. You just know that I don't know what the correct answer to all permutation of the input is, but at least I know with this input I want this answer. So you only need to have one to figure out your wanted behavior in one instance, right? The weakness of this is that as the kernelity go up, I mentioned coverage here doesn't necessarily to be true, but like how much you can trust that if your tests are green, does it still work, goes down, right? Because if you have only 2 possible inputs and you have a test for 1, then at least you have covered 50%. But if you have a kernelity of 10,000 and with 1 test, it doesn't save that much potentially. And as like post fact, if you go back to test later, it can be sometimes hard to understand the intent. Why is this that this example based test does this example try to capture a general idea that that we exemplify with these tests, or is it more that yes, at least I know that these inputs should generate these outputs, right? So what the intent was with the test can be hard to gauge sometimes, and also that can matter because if you do a change and something breaks, then you need to figure out if your implementation is wrong, probably, or if you may change the behavior so that example is not really valid anymore. Next thing, let me check where I'm at in time here. Yeah, so I will increase the pace a bit, I think. Yes, so the next one is like property-based tests. There are a lot of names for this. Fuzz test, there's a famous library called QuickCheck. Fuzzy testing. I think property-based tests is a bit of a misnomer. It's in part a really good name, and I think, but also it's a problematic because I think it can hinders the understanding of what you're actually doing. So like if you don't know what property-based tests are, is that you try to, as I showed before, you said that if you have the function add, you try to describe a property, for instance, that add x and y, no matter the values of x and y, should be the same as adding y and then x, right? And then you haven't specified what x and y is, but you know that should always be true, and which is good. It's a good way to think about a problem, but it doesn't actually test those properties. It uses that description of the property and generates example-based test and run those examples, right? And it generates a lot of them, and you can do them quite it's quite smart, and to find a lot of problems. But it's maybe a small difference, but in practice that is a really have a great impact. So the benefits of a property-based test is that I really like it because see there it creates another perspective. You have I think there's several different perspectives you can have. You can have, with this input, I want this output, right? The behavior. If I do this with my machine, I want it to spit out these numbers, which is great. The other perspective that I think is really powerful is with the types, right? You can say, okay, I want this to be like an integer or a string, and then I have a compiler that enforces that, so that is always true, right? So I can reduce the space. And another way to think about that is I reduce the kernelity of that value, right? Because instead of being everything at once, it's only this thing. But if we think about properties, I think there's another way to think about the problem, which I think is really helps both the creativity and also a good tool in the process of understanding the problem that you're trying to solve. So it's a good tool to reason about the problem, and it can also capture the intent in a good way, because it's really clear that I want the code to have this property. And of course, you can add a lot of more rigorous both terminology and both tools and thinking into that to express those properties in a very rigorous way if you want to, or you can just say that add x and y should be the same as adding y and x, because the order doesn't matter, which is great. And this way it can reduce in some scenarios greatly reduce the number of tests that needs to be maintained and changed or updated. Some weaknesses, again here, since we don't actually test the properties directly, we use some framework or a library that generates example-based tests. We have the same problem, right? When the cardinality goes up, if let's say we have a type that can have 1,000 different values, so the cardinality is 1,000. If I generate 800 tests or 900 tests and they all pass, I think we can be quite, or 999 tests, then we'll be quite happy that, okay, probably it will works, right? But if we have a type that could have that has a cardinality of 10 million, as this system work, we will probably still generate a few hundred or a few thousands different example-based tests every time you run the tests, which means that you will test very thin slice of all possible different values, meaning that you don't really know if that property holds anymore. You express it as you have shown your intent, but that is not actually what happens. This can go that, in a sense, the higher the cardinality goes up, the more the expressed tests lie, right? And that's a good thing about the example-based test, because usually they only say, with this input I should get this output, and I do. They don't try to say anything else, or they shouldn't try to say anything else. But with this, they say these functions have these properties, and that test is green. It's easy to start thinking that protection is as good as the compiler, for instance, which is not. And at the same time, if you have very low cardinality, it's potentially not especially useful, because if you only take if you only have a bool as input, the need of generating these a lot of different example-based tests are greatly reduced. Of course, they can still be a good way to think about the problem, right? What kind of, if you increase the cardinality in the future, maybe the properties will still hold. So low cardinality doesn't automatically means that fuzzy testing or property-based testing is useless, but there is some risk that is not. And also, I don't know, in my opinion, it's not enough to only have property-based tests, because you still need some example-based tests to both as a sanity check, and also if you take add, for instance, it's, or maybe not add, but if you take arbitrary function, it can be possible that even though if all your properties are true, it's always generate the same answer, for instance, or something like that. So, but if you have good properties and a handful of example-based tests, you have coming a lot longer than just the property-based tests. Yeah. So we have the example-based tests that have their benefits of being very concrete and specific, but both intent and the test very little, right? And then we have the property-based tests that expresses the wanted behavior in properties, which is good. It helps us reason about the problem. But the best test, as the best code, is the test that we don't need to write. And I mean, one way is just to have basic types. If we have integers and string, as I said before, if you say that something is an integer, you already reduce the cardinality by a lot, right? From infinity to 2 to the power of 32, right? So that's one way to avoid needing to write tests. If you take a very dynamic language, which has their benefits as well, but then if you have a function called add, if the inputs can be anything, you need to, okay, if the first parameter is a string, what do I do then? And then if the other one is a number, and so on, then you have a lot of tests if you want to ensure and decide the wanted behavior. So you could either scrap the code, just remove it, and of course that is easy to say that, oh, that here is metrics is important. If something is never used, you can think about, does this bring value? Maybe people just don't find it, but I think the more pragmatic or more useful way of thinking about scrapping code is to think about the algorithm or the pipeline that we have that solves the problem. Can we remove this step by looking at the problem from a different way, or having the data structure in a different way? For instance, if you take a very naive example, if you have a list with objects, and each object has an ID and then some sales state, for instance, and you only want to have ensure that you have one ID, you can write a lot of tests on that output that list, right? But if you get a dictionary instead, or a hash map, you know that with the ID as the key, then you know that that's going to be true. Another way is to reduce the cardinality. If you have a function that takes in more than it needs, then you will have a much higher cardinality. You can think about what do I need and what do I do not need, and also the cardinality of, even if you have the same number of parameters, can I express the legit or valid values in another way? And this is another way to say, okay, can you increase the types or have stronger types? And what stronger type means often in a more general sense is that you have a type that lowers the cardinality the most. So if you want to add restrictions to what kind of values your thing can be, right? You restrict of all possible things you can represent, this only can be in this space. And you want to have that as small as possible. And of course, here is why I personally think I have a very strong type system is really important. And you can when you can use proofs in other way in different ways. Is a great in great library in Haskell called GDP. Goes to the part of proofs. I won't go into it here, but regardless of how you do it, the great thing about this library is that you can help the type system where the type system fails. For instance, Haskell has a much better type system than many languages, but I say it still has a lot of shortcomings, or a lot, yeah, when it compares to what I would wish it would be able to do. And that the GDP library is a really good tool to bridge that. And the cost of the stronger types, if you want to increase how strong a type is very language dependent. And so if you have, of course, if you have a system that is non-typed, if you take JavaScript, for instance, or that has at least a few one type, but if you want to add layers on top of that, since it's not designed from the start, you have to maintain those layers, in a way. But even if you have a language that has a compiler and types, then that compiler could be not very competent. And then, of course, if you want to do more than just having this is a string and this is a list, then it can be quite costly. And with cost, I mean both maybe runtime cost, but also how much hassle and how much boilerplate it takes to generate and maintain these types, and how easy it is to use them as a developer, and how much does using those techniques in that language impedes on understanding the code and stuff like that. For instance, in most typed functional programming language, to create a type is a one-liner if it's a simple type. A lot of best practice in if like C#, if you have like linters and stuff, they want each like class in their own file, and there's a lot of boilerplate, and you need to, of course, some things can be done, but they are generally more costly. And this, I won't dwell on this, but this is if you just take, and of course, it's easy to take JavaScript as an example. I kind of like in certain areas as well. So I'm not a hater. I will never write the application with it, but it has its uses. So this is not my example. I found it from a quick image, quick search. But here it has like implicit conversions that generates interesting results. And what I want to highlight here is that if you have a value, let's say the first one that is a string that is 5, depending on what happens, it can actually be both a string and a number. So the cardinality goes up in a sense, even if it doesn't do that in a more theoretical sense. Since string has infinite cardinality, you can argue that it doesn't, but in practical terms, I would say that it does. Another example is that we're going to go through a few iterations. So if you have an email input, so you want to have an email, you could, the first example here, type email input equals to string, is to say that email input is another word for string. Meaning that this is for a text box and in a hypothetical application in the front end. So a person have typed their input, their email into a box, or but then you want to have a validate. You want to validate if you're going to do submit. You only want to have a valid email. So you can create a new type that takes either there's a valid email and there's a string, and then an invalid email and then a string. But you see that here we see that both valid emails and invalid email takes up the same space. They have the same cardinality and have a total overlap of the values. So if we have a value of string, we have no idea of telling where it should belong. So we could do another thing, say, okay, we have valid email, and then it's email, whatever that means. And that means that we have shrunken, instead of having all strings, perhaps we have a type that ensures that it's that it follows the rules for email, or an invalid email that is a string. The problem is that a string contains all valid emails. So the last one we could do to really make sure that the types are different depending on what we want to do with it is either we have an email or an invalid email, meaning that in the type, if we have the type instance of the type or a value of the type of invalid email, that can never be a valid email. And I think this helps because the next step and the step after that, when we want to do something with the values, we really reduce the number of things we need to test, because if you have want to email to these things or whatever, we don't need to have a check in that function, check if this is a valid email, because we know that because of the input. So we don't have to write a test. What should the behavior be if email is invalid or whatever? And this is my totally scientific thing, but this tried to capture this. So we have on the y-axis we have the cost of doing it, and on the x-axis have the knowledge capture, or the how strong the types are. So if you go to the right, the strength of the types increases, but if you go up, the cost of doing those things increases as well. And I think this is the reason why I like Haskell and Elm, and of course Idris, and we have more very niche languages, Agda and Coq as well, that can really express a lot without having the cost going to the roof. And of course Haskell, if you want to push it very, very far, or further than a lot of other languages, it starts to get really expensive as well. So if we try to put it all together, I would say that if we write example-based tests, for before this input, does it have the correct cardinality? Can we reduce it? And then could this example be expressed as a property? That's something, okay, do we try with this example-based test trying to capture a property? Then maybe we should write a property-based test. But also, if we have a property, could that be expressed in the types? Because then we wouldn't have the need of this test. Then we don't then we don't need to write it. So if we follow these steps, it creates a bit of a Goldilocks zone for the property-based tests, and that is if it's useful enough, but it's too costly to add it to the types, right? Because if it's cheap to add it to types, that is better, because then we don't have to maintain the test, and the compiler will enforce it 100%. So we have that as a tool when the cost of expressing a type, or if the compiler we have cannot do that, or the cost becomes too high, whatever your tolerance for that cost is. However, even if it's outside that Goldilocks zone, it's that we still have other benefits of just thinking about the properties from that perspective, right? Even it doesn't matter where we test or enforce that, to just have that mindset when you start with a problem can be good. And a combination, each type gives some advantages. I can just say for us, historically, we have we have example-based test and property-based test and a lot of things in the types. But I would say that we have captured a lot of the type in the types, and we have a lot of example-based tests to ensure that, especially on the API level, to say the JSON should look exactly like this, and more like scenario-based testing as well. But it leaves that we have much fewer property-based tests because we have pushed it over the edge continuously to the types, right? But some things are too expensive, or the Haskell has not good enough type system to capture that in a good way. So another key point, that cardinality is important both for implementation's sake, but also for testing. And if we reduce the cardinality, we reduce the need for tests. And the stronger the type system, the more the cardinality can be reduced. If we have a type system that can express this is a list, or and we go from there to a non-empty list, or we go to having a list with an even number of elements for some reason, right? So each time we do one of these steps, that the cardinality is reduced, and we reduce the number of tests. And the stronger the type system in general sense, the lower the cost is as well. So we can use this tool more. Yeah. So that was it. So we have questions.
Much, Mikael. Thank you very much for your presentation. Very nice. Let's see. I haven't got any questions so far in the chat, but I'll start shooting away questions to you.
Yep.
Did you consider any other languages when you started up your company and your solution? Or maybe you started with some and then went to Haskell, Elm, or...
Yes. So before in my career, I've worked with a lot of different languages. Yes, before this company, I worked in the .NET like thing, and I knew that I didn't want to work with that, to be honest. And I wanted as strong as possible the type system, but I wanted still to be pragmatic and working in a real world solution, like real world setting, right? And the truth is, there wasn't really many contenders. There was like I looked at the JVM to have some languages. They're not very. There are some communities that have like ported Haskell, but there's not very active. So when it comes to the back end, there was not really. I evaluated a few others, but Haskell was I think the most pragmatic of the more competent languages. When it comes to front end, I think there is no better choice out there. It's so because it's really focused as a language, right? It says it's to create front end applications, and it's really opinionated. But I think everyone that I met that works on the front end is really productive in it. So that was a much easier choice. Of course, none of those languages and communities are perfect, but they are. I think they're especially they're a lot better than many others.
Yeah. And then, did you get any questions from your investors or point of view on the language you selected? They were like, Haskell, we never heard of it. Will you find developers, or did they care at all? Or
no, when we started up, I wrote down my analysis and the reason to go why we should go with the functional languages, and it boils down to that I think the developers or the product department or engineering department, whatever you want to call it, should be a business enabler to be able to create business opportunities. And I think that using strong types does that best. So I wrote it, but mostly for myself, because it was a non-trivial decision, right? Since it's not mainstream, I felt that I really should think about it before going ahead, since it's quite a lot of money and a lot of people's time that we all invest in this to make this fly. And in our case, I think what we work with, it's really important that we succeed for like the climate and all the other factors. So I didn't take it lightly. So I generated a few analysis documents, but mostly for my own sake.
Would you redo any technical choice today? Like if you could back up and say, okay, with this experience now, I would choose some, something else, or would you go with the same setup you have today?
No, I think that has surprised me the most. I mean, we have changed a lot when it comes to inner dynamics, and as I said, we have rewritten stuff several times. And again, right now, the teams are working with like changing one major like core part of the application. But when it comes to the main pillars like Haskell, event sourcing, and Elm, if you take those pillars, the answer is no. I think they work really, really well. Would I like there to be a new like Haskell 2 or that some other modern alternative came up? Yes, I would. I think Haskell is far from perfect, but I think it's much better than a lot of other things.
Yeah. Maybe you mentioned it, but which database do you use? I mean, it's not.
We use Postgres. Or so we have there is like event source specific ones. We don't use those. That is not for once. We have a few parts that are not event sourced, which is great. Those are the parts that have created headaches for us. So we have removed them over time. But also we started with Postgres. It was just that start simple. So that is not the result of long, like a proper analysis of should we go with like event source based database, to be truthful.
Event sourcing, I mean, it's I love the concept, and you can use it. I mean, it doesn't matter really what type of programming language you use. You can event source exactly. Was there any did you have any issues with your dev team for people to grasp that, or did it come naturally as they came from functional, or they're into functional programming? Event sourcing would be, because I tend myself to find when I work with the database or database people, they see it like you create this record, you change it, it's mutable. They going into this like no, we for every instance we create new.
Yeah, so I think for us, of course, we have a selection bias when we've hired that helps this, but for us, there's in these three pillars, I think there is some synergy or like that hooks into each other that makes it like fit really well together.
Yeah.
If I will come back to the database shortly, but as like if you start with the front end, we have this conceptual loop we have the view, we have the state that is connected to a view, and the view generate messages to update the state, right? And the neat thing is when we zoom out and have the front end as the view, we generate commands to the back end, which that calculates a new state that we send to the front end. So we actually have more or less the same loop when it comes to the front end stuff, or for the web application stuff, in several different like abstractions, or like both when we look at the system as a whole, or in the individual part of the front end. And that makes that hook into very neatly with with event sourcing because we have a command that generates an event and we have a list of events, and both Irmin and Haskell, like immutability is a really big part there. So we have taken that further, and also like in our field, like orderability is really important, and who made what where, and we get that all that for free. So I think since immutability was a really key part of what we do, then those choices fit really well together. And when it comes to the functional program minds, I mean, if we have people like fold or stuff like that, like in a very naive or like essential way, the event sourcing is just a fold over the events, right? So it fits really well with that with that paradigm.
How come you came into functional programming? You mentioned you worked with .NET before.
Yes. Oh, yeah. So I worked with .NET and Python and a bunch of other languages as well in different, and PHP for like a long time ago. And I think it's several different reasons. One was I worked a lot with processes in some of where I worked. Even though it started with technical choices, it always came back to processes, because okay, now how do we want this to work, like our internal and to take a very concrete example, when we started with F# in another place. In F# you can do side effects wherever you want, right? It's one key good thing about F# is a good gateway, because you can just start like incorporating functional ideas like piece by piece. But also that means that you can't really trust if you have add X and Y, if that is pure or not. You don't know that. So then we said, okay, we put all the pure thing in a folder called pure, and then but then you have a process problem, because then everyone need to follow that, and over time that is unmanageable. So to avoid having those problems, to avoid having to deal with things like how should we deal with null, or how should we deal with this? So I have a strive to remove those problems entirely in us on a systemic level, and I think that drove me to stronger and stronger types, and currently functional programming language are the ones with strongest types and best compilers. So I think for me those things are more important than it's functional. But if you have those things, I think functional programming is like a natural thing to jack in, because a lot of other things don't work with immutability and really strong types.
True. Last question: have you used QuickCheck? In the current in your current in the current solution, or have you used QuickCheck?
Yes, let's see. So I can't, but yes, and I can't remember now if we use. Currently, we use HSpec with QuickCheck together for the property-based test. Yes, so for the property-based test, I think we use QuickCheck. Yeah.
Yes. Interesting. Again, thank you very much, Mikael. There's no more questions. People are shouting in the chat. Great presentation. So thank you very much, Mikael, again. And thank you very much.
Yeah.
With that, everyone, thanks for tonight. Thanks for joining. Thanks for all your questions and your engagement in the chat and on the Discord channel. We'll see you all again on 23rd of May. So with that, have a nice evening or day wherever you are. Goodbye.